In this problem, we're not really doing a comparison of time to a dependent variable. What we're doing is we're comparing one state's population as a function of another state's population. So the way this data is usually gathered is we can look at Ohio's population as a function of the year and do the same thing for New Mexico, and then for those particular years we match up the Ohio population with the New Mexico population. So that's usually how this is modeled, and that's how I modeled it. And we know that this model that gives us the population of Ohio in millions of people as a function of the number of people in New Mexico in millions. So let's first find and explain one of these values. This is kind of a trickier one, especially when the input's not time. So O of 2 we want to find, which means we're going to evaluate the this equation here for an input of 2. Now, before we do that, let's talk about what N represents. That's the population of New Mexico, and this is in millions. And then the output, O of N, will be the population of Ohio in millions. Okay, so we want to plug in a 2, and we'll evaluate this in our calculator. Probably not worthwhile to plug this into our y equals right now, since we're only using it for one output value. I'll raise that to the second power, and I get 11.56 roughly. So we'll just write down 11.56. Now what does this mean? Well, N is the population of New Mexico. So when the population of New Mexico is 2 million people, it is estimated that, because remember this is just an estimate, that the population of Ohio is what do we get, 17 or 11.56 million. Okay, so very nice. So that gives us a relationship between two populations, and we can see that obviously New Mexico has a very low population in comparison to Ohio. It's roughly about 1/6 the size of the population. And now we want to find the rate of change. Okay, so what's our rate of change going to be? So rate of change units are the change in output over the change in input. So output is the population, or we don't even need to write population, we can just say millions of people in Ohio. And the input is the millions of people in New Mexico. So our rate of change is going to be in millions of people, millions of Ohioans per millions of New Mexicoans. New Mexicans, I guess we'd probably say. And to find this rate of change, we're going to use our standard, in this case, we're using O of N, so we'll do O of N plus H minus O of N over N plus H minus N. And we want to find out what happens to this rate of change as we make the value of H really small. So I'm going to copy down what I know, find out what I need to plug in here. So number one, O of N is the equation I was given, which is 10.1 times 1.07, whoops, 10.1 times 1.07 squared. 10.1 times 1.07, excuse me, to the n power. So O of N plus H is actually pretty easy. All we need to do here is replace N with this, and there's not really anything to FOIL here. Put an N plus H up here, except the trick that we're going to do is going to involve using a property of exponents here, and we're going to do it for a pretty good reason. So what we'll do is we'll realize that as a review, that if you take x squared times x cubed, you get x to the 5th. Okay, so we add the powers, right? So we do basically that's just x to the 2 plus 3. Well, in general, we can say that any base to a power times the same base raised to any power is equal to the same base raised to the sum of their powers. Right? And the reason this just occurs is if I have a squared and a to the third, then that means a times a times a times a times a, which is the same thing as having basically a multiplied by itself 5 times. Now similarly, I can go backwards. If I have a to the b plus c, then there's no reason why I shouldn't be able to split it back apart if I want to. I put it together, I want to be able to take it apart. So here we have that same setup. We have something raised to something plus something. So all I'm going to do here is I'm going to write 1.07 to the n times 1.07 to the h, and I'm going to leave it like that, because that really just separates my n's from my h's. Okay, so what I'm going to do next is I'm going to plug everything in. So I'm going to write down the fact that I'm trying to figure out my little reminder that I'm going to make h0 at some point when I can. 10.1 times 1.07 to the n times 1.07 to the h minus 10.1 times 1.07 to the n. And on the bottom, as usual, my n's will cancel out and I'll be left with an h. Because remember, this is just the change in x on the bottom, and the change in x is h. That's the horizontal distance between our 2 points. Now, the one thing you're going to notice that we're going to factor out this 10 times 1.07 to the n power. The reason we do that is because even with very, very, very small values of h, this ratio calculation-wise becomes very bizarre, and it's almost unstable when you start picking values of h. Without going into too much detail why that happens, we're going to simplify our lives a little bit, and we're going to say, okay, well, let's just go ahead and factor out what we can. So the reason we split this apart is we can factor this out from both pieces. So I can do 10.1 times 1.07 to the n multiplied by what's left over, which I still have this guy, 1.07 to the h. I've divided this guy out, so now I have just a 1 there. Remember, it's not a 0 since I'm dividing it out. There's got to be a placeholder for it because I've got to be able to multiply it back in if need be, and I should still be able to get back to what's in the numerator. I'm not changing it, I'm just manipulating it a little bit. Okay, and this is all over h. Well, notice that this guy right here, 10.1 times 1.07 to the n, does not really depend on h. Okay, so you can think about this as, if you'd like to, you can pull it out front of the limit sign, because whatever, as h approaches 0, that's not going to change the fact that you're still going to have this piece here. So without, if you prefer just not to have to factor more things out, why don't we do this? Let's go ahead and now think about what's happening over here. So here's our critical piece. And the reason it's critical is because we can't really factor out an h to cancel it. I've got an h up in the numerator here, but here h is a base. So there's no way I can actually do any cancellation here. This is one of the disadvantages of our method, is that it doesn't really work that well for exponential functions, this whole f of x plus h minus f of x over h idea. So what I'm going to do instead is, this is where I get to use some estimation. So we're going to pick small values of h and see what happens to this ratio right here. So pick small values of h. This is really similar to what we've already done in this class, except that we haven't done it like that, quite like this before. So what I'm going to do is I'm going to make a little table here, and I'm going to compare what happens to this ratio when I change h. Now I'm not going to pick a lot of values of h because I don't want to have to compute too much, but I will pick negative 0.01, a point that's really close to 0, but that's to the left of our point of interest, and I'll pick positive 0.01 since that's on the right of our point of interest, and then that tells me that this guy is probably somewhere in between here. So all I'm going to do is I'm going to take 1.07 and I'm going to raise it to the power of negative 0.01. I'm going to subtract 1 and I'm going to divide it by the h that I'm using now, which is negative 0.01. That tells me that this ratio, when it's really close to, when h is really close to 0, this ratio is going to be 0.068 roughly. Now, from the other side, if h is really close to 0, but on the positive side, so remember this is horizontal distance, we always pick points that are to the left and to the right, just to make sure that our guess isn't too far off. And you can see here that this also rounds to 0.0678. So, excuse me, 0.068. So, without rounding too many decimal places out more, I'm just going to say, hey, it looks like this guy, for values of h close to 0, as h approaches 0, this guy right here becomes roughly 0.068, or approximately 0.068. Okay, well now I can remove my little limit as h approaches 0 and just say 10.1 times 1.07 to the n times what happens to this ratio when it gets increasingly close to 0, which is 0.068. And that's it. We are basically done. Even though this is an approximate answer, we just found O prime of n. We did it a roundabout way, but we took advantage of what our notation meant, which is get h as close as possible to 0. Well, we could have gone negative 0.000000001, but there's not even that much of a difference between this ratio at negative 0.01 and positive 0.01, so there'd be no sense in trying to get much closer unless we wanted way more decimal places. But we don't necessarily care. We want something that's fairly approximate. Now our goal was to estimate what's happening to the rate of population at 1, 1.52, and then explain. And O prime of 2. Now before, I'll have you notice one interesting thing here. Notice that the base is 1.07. Look what happens when I take, not that you would just do this, but look what happens when I take the natural log of 1.07. I get approximately 0.068. And with all these digits, look how close these numbers, all three of these numbers are. It's not a coincidence that this guy right here is roughly the natural log of 1.07. In fact, we're going to find out that the derivative of a exponential function is a constant multiple of itself, and that constant multiple is the natural log of the base. So as a side note, and this will be a rule that we learn later on, as a side note, the derivative of, let's just call it f of x, if f of x equals a times b to the x, so a and b are both constants with certain characteristics, f prime of x will be the same thing, but it will be multiplied by the natural log of the base. So this is actually a rule that we're going to establish, and you don't have to go through all this work. Here's the actual rule itself. And that's kind of just from observation. Okay, so back to our goal, finishing things up. We want to find O prime of 1. I'm going to take advantage of my calculator, and I'm going to type in the slope equation, just so it's all here. 7 to the x times 0.068. I'm not going to use the ln of 1.07 because we're not really supposed to know that yet, but that's okay. And I'm going to go to my table. I'm going to type in 1, 1.5, and 2, and I get 0.73, 0.76, and 0.79. 0.73, 0.76, and 0.79. Should put squigglies on these. Now, what are these units? These are millions of people in Ohio per millions of people in New Mexico. So what's happening here? And I think Part C wants us to address that. Part D, what conclusions can you draw from your answer in C regarding the Ohio's population with respect to that of New Mexico? Well, we find out that actually the relationship is such that the per million people in New Mexico, at first, the number of people in Ohio, so if we increase the population in New Mexico by 1 million, while there are exactly 1 million people in New Mexico, the number of Ohioans is going to increase by only 0.73 million. But as the population of New Mexico grows, notice what happens. The number of more people in Ohio grows a little bit more per 1 million people more in New Mexico. When there are 2 million people in New Mexico, the population of Ohio only increases by 0.79 million people. So it looks like not only is Ohio trumping New Mexico in terms of population size, New Mexico is growing a little bit faster, but relative to Ohio, as more people move into New Mexico, the growth rate isn't that much different. In fact, at some point, if this keeps on going, we'd expect the ratio to be 1, meaning for every 1 million people in New Mexico, 1 million people move into Ohio. Will this happen? We don't really know. This is just a model, and we take it with a grain of salt and kind of see what it maybe tells us.